Well, welcome everybody for the afternoon session on genes and health. And it's my great pleasure to welcome the first speaker, Damian Roqueiro, from the ETH Zurich, Basel, which is a strange place, and he will talk about in silico phenotyping via co-training. No, it's not a strange place, it's an internal joke, because of course the ETH has now an outstation in Basel, and we always make internal jokes. So. In silico phenotyping via co-training for improved phenotype prediction from genotype. Looking forward to your talk.
Okay. Good afternoon, everybody. As the introduction went, I work at the Machine Learning and Computational Biology Lab at ETH Zurich. And our presentation is titled In Silico Phenotyping via Co-Training for Improved Phenotype Prediction from Genotype. So let me start with the motivation for our work. What we want to do is construct a classifier, more precisely a genotype classifier, that will be trained on genotype information obtained from a group of individuals. And for each of these individuals, what we will have is information in the form of SNPs, in addition to a disease phenotype label. Now, the classifier will be trained on this data, and then when we receive new genotype information, it will be able to predict the phenotype for these persons. Now, such a classifier, as you may imagine, is very important, in particular because it can be used for disease diagnosis and therapy. Nonetheless, it has some constraints, and the main important one being the fact that in order to perform accurately, it requires a large amount of label examples. So nowadays, that doesn't seem to be a problem in the sense that we have an increasingly larger availability of genotype data, but the bottleneck seems to have shifted from the genotyping to the phenotyping. That is to say, we have more genotype data, but we lack the disease phenotype labels. So the question that we want to answer is there a way to boost the performance of this type of classifier when we only have few label examples? And the answer is yes. I will try to convince you that the answer is yes, based on a method called co-training. So let me summarize what co-training is. It was first proposed in 1988 by Bloom and Mitchell. The main idea is that we have a data set that can be divided into two types of data, what we call the labeled data and the unlabeled data. In this case, each data point can be described by a set of X features, and the label in the particular case is binary, either yellow or blue, and as you can see, some data points here do not have a label, and those are marked in white. Now, co-training requires a partitioning of the feature space in such a way that there are two mutually exclusive views of the features. Now, if we take that from the notation point of view, that means that a labeled object X can be defined as the X1 component of the data, followed by the X2 component and a class label. The next step in the methodology requires the creation of two different classifiers, each of them on these mutually exclusive views. And the idea is to proceed in an iterative manner such that we take, for example, classifier H1, trained on the label examples and using the exclusive view X1, and the classifier will assign labels to all the unlabeled samples. Now, one of these samples is going to be the one for which the classifier is most confident, and then this label will be moved from the unlabeled set to the labeled set. Likewise, now we move to the classifier H2. The difference being now that the labeled set has grown. Now we have the 4 original true labels plus the one that H1 has imputed, but we proceed in the same way. The classifier assigns label to all the unlabeled samples. The most confident one is moved to the label set, and we alternate between the classifiers until certain stopping condition is met, normally when the set U of unlabeled samples is empty. Now, there are two important requirements for co-training to work. Those are stated in Bloom and Mitchell's paper. The first of them are that small x1 and small x2 have to be conditionally independent of each other, given y, and I'll talk more about this later. The second requirement can be summarized in a way that the two mutually exclusive views have to be sufficient for us to train two different classifiers that are good enough to classify points in D. Now, this good enough idea means that we can have one classifier being weaker than the other one, but both of them have to be better than random. So the methodology that we propose is a variation of co-training, but let me illustrate here how we applied this method on a migraine data set. So on this data set that was obtained from two Dutch cohorts of approximately 2,000 patients, we have two disease phenotypes, migraine with aura or migraine without aura. These have been very well studied, even the genetic components of these diseases. They have different disease outcomes and therapies. In this case, we're going to use the binary labels. So to summarize the type of data that we have, as I mentioned before, firstly, we have a disease phenotype, either aura or no aura, followed by what we call clinical covariates. In this case are, for example, clinical information such as, is a migraine attack have a pulsating quality? And then finally, we have genotype data in the form of SNPs. Now, the reason why I highlight these last two is because both of them fit the spirit of co-training in the sense that they are mutually exclusive views of each patient. Now, we have an assumption about an implicit price tag of the data, and we use this to derive our methods. The first assumption that we have is that the disease phenotype is the most expensive one. It's a diagnosis, it requires the expert opinion of a doctor, and it's hard to acquire. Normally, doctors, in order to base their judgment, they require tests from the patients, and we call those clinical covariates, and we deem them the second most expensive type of data. And the most inexpensive one, in our case, we assume to be the genotype data. Now, what's important about this slide is that we know for a fact that clinical covariates are very strongly correlated with the disease phenotype, with the diagnosis that a doctor makes. So we want to exploit that correlation in order to use clinical information to impute missing disease phenotypes. Now, to reinforce this idea of why we think that genotype data is the most inexpensive one or will be in the future, well, you all have seen this chart before that plots the decay of whole genome sequencing over the last 14 years. But what's important here is what I highlighted in the bottom is that we don't have to do full genome sequencing. Nowadays, we can obtain approximately more than 700,000 markers through genotype arrays for a cost of $100, $110 per sample. So this radically is going to change the landscape of how disease diagnosis is being done in the clinical setting. So continuing about the types of data, we have these clinical covariates that I mentioned before, and the way they are highlighted in this particular case, they have been clearly defined by the International Classification of Headache Disorders. So you have here an excerpt on the right of what these guidelines look like. They are in the form of a questionnaire that patients have to answer. So for example, in our case, they're going to be binary traits. If you look at attack length, it actually corresponds to answer of question B that says, did you have a headache attack that lasted between 4 and 72 hours? Yes or no? Similarly, we have information about, is your migraine attack aggravated by physical exercise, and so forth. In regards to the genotype data, with it's approximately 500,000 SNPs. What we did is the standard coding of the allele information using the additive method where we code the values into 0, 1s, and 2s. And we performed some pre-processing and filtering. The pre-processing was to make sure, first of all, that there was no population stratification, which we were able to confirm. And the filtering was just to remove SNPs due to minor allele frequency and other things. And in the end, we ended up working with a set of 460,000 SNPs. So let me summarize how our methodology works in this sequence of slides. The first step is what we call data preparation. So we have this large migraine data set that we randomly partitioned into 3 sets, namely what we call a training set, a co-training set, and the evaluation set. We also refer to them as Roman numeral 1, 2, and 3. The idea here is that a patient will be randomly assigned to each of these sets. Now, there's an assumption that we made, and that's to illustrate how the co-training method works, and that is that we assume that the co-training dataset will not have disease phenotype information. There are no labels. Similarly, in the evaluation dataset, there are no clinical covariates. So our method is a two-step process. In step number 1, what we do is we actually impute the missing labels that I just told you that we were assuming didn't exist. So we create a covariate classifier. The covariate classifier is trained on the training dataset, and it assigns all the labels in the co-training dataset. For that, we use what we are called bagging predictors, a method described by Leo Breiman in 1996. Once these labels have been imputed, then we construct a genotype classifier using the true labels of the training set plus the imputed labels in the co-training set. And then we can assess the classification performance of the classifier on the evaluation data set, because there we do have the true labels. Now, as you may imagine, creating a classifier with 500,000 features is quite challenging, so we implemented a univariate feature selection method. So to put it in a nutshell, the idea is that for each particular SNP, we tested the correlation of the genotype information of the SNP with the phenotype information. Then we obtained the p-value for the Pearson correlation, and we ranked the SNPs in ascending order of p-value. And from that, we took the top 2,000 SNPs. If you recall from when I described the co-training method, I mentioned that there were 2 requirements. One of them was that the classifiers could not be correlated. And the idea behind this is that there's nothing to gain from this method if both the covariate and the genotype classifier make the exact same predictions. So we wanted to test if that applied to our migraine data set, and what we did is we created 100 random partitions of the data, a training set and a test set. For each of them, we constructed a classifier, and we tested that in order to determine not if the classification was correct, but in order to compare the 2 predicted classification vectors of the covariate and the genotype classifier. And as you can see below, the correlation was quite low. In fact, we computed the Manhattan distance, which happened to be quite large, with a small variance, and that is shown in the histogram that you can see there on the right. So this was a good sanity check for us to know that the method is applicable, in particular to this data set. So before I go to the results, let me show you, or let me introduce two classification performance metrics. And the first one of them, we call it the lower bound, but it should be placed between quotes. The idea here is that we want to see what is the worst case scenario in which a genotype classifier can be trained. And that corresponds to the case when we have the least amount of label data. In this case, only using the labels in the training set. We call that the lower bound. On the other side of the spectrum, we have what we call the upper bound. And here, what we do is we train the classifier on the largest amount of true labels that we have. Now, if you remember, I made the assumption that we did not have phenotype information in the co-training set, but in reality we do. So this is a good way for us to determine what is the best performance, classification performance, that a genotype classifier can have. And our co-training method cannot do any better than this upper bound. There's a third performance metric here listed at the bottom, but I'm going to skip it in the interest of time. So I want to draw your attention to this table, particularly the first row, the last row, and the highlighted row, which is the performance of our algorithm. The idea being here is that we are performing more than 7% better than the lower bound. Of course, this is not stellar performance, but it brings us closer to the upper bound, and it is much better than random guessing. Now, the previous result is more of a static snapshot, but what we did is we wanted to see what are the effects when we vary the size of the data set. For example, when we fix the training set and then we increment the co-training set, and you can see this in this figure here. The table below shows what happens when we add more unlabeled samples from 40 to 70%. And fortunately, the value of the mean AUC increases. And this is exactly the main motivation of our method, in the fact that the more unlabeled data is added, the better the final genotype classifier performs. Similarly, we fixed a large amount of data for the co-training dataset, and we shrunk the true labels, and as expected, the performance decay, but it's not so bad. In fact, if you look at the last value, when we have only 1% of true labels, we are performing at 0.60%, which is much higher than the lower bound that we obtained here with 10% of the data. And finally, we put all of those pieces together to get a more dynamic view of the data, of the results, and we created a 10 by 10 grid in which we increased the size of the training set and the co-training set. But what we did was to add a twist to it in which we do not report just the AUC, but each value of the grid reports a gain, meaning the AUC that we obtain from co-training minus the AUC that we obtain from the lower bound. So the heat map that you see here reflects those results. And what's important is, in particular, the first column that basically says we start with a small set of true labels, and the more unlabeled samples we add, the better the algorithm performs. And this white area that you see here, whitish, yellowish, basically says that when the set of the true labels is big enough, and we are not adding too many samples in the co-training set, then the performance doesn't do any better from the baseline. So to summarize, what we presented here was an approach to in silico phenotyping. The idea is that we want to impute disease phenotype using genotype information and clinical covariates. And the main goal of this project was to be able to augment data sets so that we can train models for phenotype prediction in a better way. Now, the take-home messages from this presentation, I think, should be what are the factors that affect co-training. In particular, the first one is that the size of the original training data set must be small, meaning we have to allow for improvement by augmenting the number of labels. The second is that the co-training data set must be large, meaning, and we saw it in the heat map, if we only add a few samples, there will be no increase in the classification performance. And then finally, the clinical covariates and the genetic data must be predictive. They should not be redundant. So what we feel that the future may hold for this particular type of analysis is that nowadays we have large sequencing projects that are creating ever more amount of genotypic data. In particular, we have biobanks that are collecting more samples, and these samples, most of the time, can also be related to health record information. For example, the UK Biobank is a very good example of this. And we believe that this in silico phenotyping approach can make use of all this data in order to improve disease phenotype prediction with the ultimate goal of using machine learning to improve personalized medicine. So with that, I would like to thank our collaborators and the International Headache Genetics Consortium for providing the data. On behalf of the Machine Learning and Computational Biology Lab, I thank you all for your attention. And just one final note to say that our group is expanding, so if you're interested, please come talk to us. Thank you very much.
Thank you very much for a very interesting presentation on a very current topic. We have time for one or two questions. Please, can you please come to the microphone so people can hear you?
Hi. I was wondering, how important is it to have in your co-training set both positive and negative examples? For example, if you had a co-training set where you would only have healthy individuals, would that help you or would not that help you at all?
So in the original paper, there's a requirement about the sets having to be balanced. Now, in our particular case, we had more cases of migraine without aura than migraine with aura, and we didn't see any adverse effect, meaning we simulated the data when we assumed that both of them were 50%. But to answer your question, in order for the classifier to perform well, we need both. We need the positive and the negative examples. I do not foresee it to work when we have only one of them.
So from what I could see, there was an average correlation of about 0.67-ish. Have you tried to go back and actually look at which patients are difficult to predict? Are there any covariates you do not account for in the analysis that could possibly make it even stronger?
Yes, in fact, we don't have an answer for that yet, but what the conversation that this started was in fact, with the clinicians. They are not very confident that we can create good classification on genotype data. So what we used from our results was to try to find which ones were those patients for which we were very confident that the classifier will either classify them as with migraine, as having migraine with aura or without aura. And right now, they are in the process of determining what's interesting about these patients or not. We don't have a conclusive answer.
Thank you.
You're welcome.
Hi, so
Hi.
you're training a classifier initially to move samples from your unlabeled set to your labeled set based on observations in the labeled set. So when it comes to validation, you split the data. Have you not already seen the data that you're testing in the validation set because you've used it to sort of label the data that you're using to then try and find a phenotype for?
So the way we partition the data and that assumption that I mentioned about assuming not having the labels avoids the problem that you're mentioning. So there's not a single point when we are doing a validation using predictions on data that we were not supposed to have. So thank you.
Thank you very much.
Thank you.